Hi everyone, thanks for joining today. My name's Dave Reines from Improving. I'm a VP of Technology at Improving, and today we're here to talk about realizing the event-driven enterprise. It's something we've worked with many of our clients on for the last several years. I think since about 2014 we've been working in this architecture, and it's something that we found a lot of benefit, a lot of good business value with the clients that we've been working with. So I'll just kind of jump right into it here. Just a quick introduction. A VP of Technology at Improving. I'm personally headquartered in Minneapolis. I have over 20 years of industry and consulting experience. I focus a lot lately on cloud native engineering with Kubernetes, AWS, Azure. But streaming and real-time data has always been a core of a lot of the projects that I've been working on for the last, like I said, 5-6 years now, which includes technologies like Kafka, and a lot of NoSQL technologies as well. Elasticsearch, Cassandra, Mongo, Cosmos DB. With that ends up being the core of a lot of the architectures that we use when working with clients on this type of problem set. I have a strong background in APIs and microservices, polyglot, do a lot of Java, Spring, Node, Golang, Ruby, and those types of languages. So just wanted to get right into it here. You talk about, just want to take a step back and talk about what enterprise data integration is like at many enterprises. And it's a lot, this is a pattern that we see at a lot of companies that we work with. We've been working with a lot of the major companies, Fortune 10, Fortune 100, on implementing these patterns to help solve some of their data problems. So if we take a step back and see what we see in terms of enterprise data today, there's a lot of many different source systems, many different users of the data, many different systems that are integrating with this data. If you look on this diagram is illustrating, you have your NoSQL types with like a Mongo, Cassandra, Elastic. You have your cloud-based systems, AWS, GCP, Azure, whatever cloud-based system it might be. You have your analytics, you have your data lake, you have your reporting, you have IoT data coming into the enterprise. You have mainframe systems with the legacy data. You have monolithic SQL apps, possibly using something like Oracle or MySQL. And then you have these data integrations with various partners, whether it be file-based integrations or API-based integrations, or maybe even just a messaging type integration. So all of these things are happening across enterprises. But when we look at how that data is integrating, what we see at a lot of organizations is there's a lot of point-to-point based integration happening. And this leads to a lot of problems across the enterprise. For one, these project-specific integrations have limited reuse. So every time there's a new project, somebody says, I need to get that data over here. How do I get it? Okay, I'll grab that data from my project, transform it to my specific format, and put it into that system. And what it ends up doing is it tightly couples all these systems, which becomes really difficult to maintain across the vast enterprise. And it even increases your vendor lock-in on a lot of your legacy or monolithic systems because so many people are integrating with that data and they're doing it in a way that's specific to that vendor, which makes it difficult to move off either that commercial type system or even if it's your own legacy system, it makes it more difficult to move off of that legacy system. And a lot of times we're seeing batch-oriented processes, which really decreases the value of the data for certain use cases. The data is maybe a day old, so it's stale data. So are you reporting, or are you running analytics, or are you providing consumers of the data the most up-to-date and latest data? And with these batch-oriented processes, it's just often not the case. So we've taken a look from an architecture and what's an architecture that works with this. And we took a step back and said, what are the objectives that we're trying to solve here? So we're looking to provide near real time. Now notice the real time versus batch that we talked about, and standardized synchronization of mission critical data originating from various heterogeneous data sources in a secure, scalable, and highly available manner. So I'll touch on a couple of the words here. So standardize means that we're going to take that data, put it into a standard form, whether you call it standard model, conform model, canonical model. That type of data is what we're looking to find so that when people integrate with it, they can use that form that's standard across the enterprise, and it's not locked into a specific legacy format or a specific commercial off-the-shelf format. And again, we want to make this real-time data. We want it secure, we want it to scale, and we want it to be highly available, always available to consumers. So the enterprise event stream is the architecture that we've been working with clients for some time now. So in this model, these various systems can integrate with the event stream, which provides a lot of value to the different consumers of the data. So it's going to provide, in this case, we're actually providing a single standardized source of truth. And if you look back at this, a lot of people might look at this and say, well, event stream, that diagram looks exactly like the enterprise service bus of the older days. Well, the difference here is that the data in the event stream is persistent. And because it's persistent, it becomes that standardized source of truth that's available for consumers to consume, again, in real time. And with this architecture too, it also accommodates self-service integrations. So instead of having that project-based, I need to ramp up a project, I need to get some funding, I need to then set up a specific integration for this other system. With this architecture, we're able to set up self-service integrations. So you can build automation on data that allows people to register for that data, say I want to consume it, go through whatever governance process is required, but do it in a more of an automated fashion and automatically then immediately start consuming that data with no impact to the legacy systems. All that data is sitting in the event stream, and there's no additional impact on compute or resources within that legacy system. And again, we're integrating here with data in motion versus data at rest. The data is coming across in a stream, and it's persistent too. So if we want the live updates, we can get it, but if we want to go back and get the history of it, we can get that data as well. Really what this is doing as well is it's enabling modern platforms. Platform modernization, digitization is a huge initiative for many enterprises. And this is a huge enabler of that capability. So it's going to create public cloud enablement, real-time analytic capabilities, microservice architectures. You can start now more easily working with alternative data stores, whether that's open source or cloud-based or NoSQL-based, whatever those data stores might be. And you can also build notification and alerting off these systems, which is hugely beneficial for many business use cases. And then again, it also provides the capability to offload legacy systems. So a lot of times today, people are building APIs against those legacy systems, whether it be a monolithic database or whether it be a mainframe system. Those APIs are hitting those older systems. So now your uptime, your SLAs, or whatever the SLA of your legacy system is. In this case, we can offload that data, build APIs on more modern data stores to provide low latency queries and have larger uptimes than some of the other systems. So let's get into some of the architectural details. So if we look at what an event-driven enterprise might look like, I think this slide is focusing mainly on streaming and APIs. One thing it doesn't show is the data analytics in this slide, but that could easily be incorporated into the event stream just as easily. So from an API perspective, if you look down at the bottom of the screen, you'll see your core services. These are your core system of record source systems. This is where the system of record lies. The system of record, the event stream doesn't become your system of record. It still lives in these legacy systems that exist today. The system of record has raw data that we're pushing to a set of core data services. And when we push that core data over, we create conformed or standardized models that exist within those core data services. Those core data services then have two ways of accessing the data. One, by directly accessing via the API, calling the APIs directly, which access the appropriate data stores. And the other option too is they can also offer the data in a streaming mechanism. And that's why you see the conformed data being pushed up to the business process services layer. In this layer, they can decide either to consume data and push it into one of their data stores. For example, if they need to do more aggregation or put it into a different type of data store that's more specific to their use case. Maybe they need to use a graph database because they're managing relationships, or they need to use Elasticsearch because they're doing more search-based mechanism. They can do that, and they can aggregate the data together at that business process service level. Or some of these process services don't have their own data stores, and they can call directly to those core data services to make that data available to the rest of the enterprise and add value at that business process service layer. And then again, the experience-based services are more specific to the end consumers of the data in often cases. So you might have aggregated data that happens at that business process service layer that's pushed up to some of these more experience-based services. So you might have mobile APIs that have specific needs and specific data stores that they need specific to that mobile application. Web APIs, IoT-based services. Maybe you have installation services for IoT to install IoT devices. You have MQTT communication. All that can be done out of the event stream, both in and out of the event stream. Device APIs for specific devices that you have throughout the enterprise, IoT type devices. Custom integrations. Ideally, you don't want the custom logic for specific integrations for some of your major partners or vendors that you're willing to build custom integrations for. You want to keep that out of those business processes and core data services and build specific integration layers at that experience service layer level to provide for those consumers of that data. Web APIs we talked about, and IoT services we talked about. So again, this is a high level architecture of what some of that event-driven enterprise might look like. And then on the left-hand side, you see APIs and streaming. And I put batch in here too for a couple of reasons. Sometimes some of the legacy systems that you integrate with, just aren't ready for real-time streaming data for various reasons. Maybe it will cause issues on the data store. Maybe they can't scale to the level and they need to run it at night. That's fine. From a streaming perspective, you can access that data in real time, or you can consume it in batch. Either way is fine and doesn't have an impact on the underlying streaming data store.
Got a question for you, Dave.
Sure.
Jason asked, are there tools for centralizing enterprise architecture knowledge that you would recommend? Like tools to capture, maintain, and share between architects, business leaders, and product teams?
Yeah, no, that's a good question. I think there's a lot of collaborative tools out there. I don't have any specifically that I recommend. I think it's more so the processes that we use. Typically, we like to use when we get into that business conversation. We like to use a domain-driven design approach when talking with that business and sharing architecture with the business. So from that perspective, the tool would be just the concepts behind domain-driven design. So I can develop a shared understanding with the business leaders, with the business users, with the engineers and the architects of what exactly we're implementing, and coming with that, that model within domain-driven design really helps that discussion. So they're not talking about specific architecture pieces. Everybody's talking about business concepts. So I think that that's really important when you're having some of those discussions. Okay, enterprise event stream. So this is drilling down into the enterprise event stream and what's the processing that's going to happen in more detailed level within the stream. And if I look here, I'm going to just go back one slide here. What we're looking at here is I have this system of record and I have this raw data coming across, and I'm aggregating that data and I'm putting it into the data stores for these different domain services to make the core data services available. And that's what we're showing here at a more of a drill down type level. So we have these legacy system of record, and we use tools within the event stream that push raw topics out to the stream. And from a technology perspective, I don't have technologies or implementation technologies within this architecture, but the technology that we use 99% of the time for this is Kafka. So if you're familiar with event streaming in Kafka, this is the technology that works really well with this architecture. So in this case, we have a set of topics within Kafka that we're pushing data into raw topics. And then that raw topic goes to a source aggregator that aggregates that data, pushes it to aggregate topics where we have the conform standardized data, which then can be consumed into different materialized views. I'm going to drill down to each of these pieces a little bit and walk through it. Before I do that, so this also works really nicely for multi-source architectures. So a lot of enterprises we work with, they may have grown via acquisition or have a lot of similar systems that do the same thing or work with the same type of data. In this case, we could have multiple legacy source systems pushing to these raw topics, having a source aggregator specific to that source system, and then pushing to the same aggregate topic. So now I've got a view of that data from multiple systems available for the enterprise as a source of truth. So I can build materialized views off that. I can build my analytics off that. I can accomplish, APIs and the various use cases that we discussed on a single source of data versus, having to deal with both legacy systems. So we'll talk a little bit about the legacy sources that we've worked with. Some of the common enterprise data sources. DB2 is a really big one out there. People are on the mainframe still. They want to get that data off the mainframe in real time. They want to build APIs to help reduce their MIPS, to help save some costs. So that's a big one that we work with quite a bit. Obviously, Oracle, SQL Server, MySQL, etc. There's different type of connectors that connect with these different data sources and provide that change data capture capability to push that data into the stream in real time. So change data capture, as I just mentioned, publishes that data in near real time. The nice thing about change data capture is the way that it works off the database transaction logs. So it really minimizes impacts on the source system. You're not doing large queries periodically on the system that ends up causing additional performance hits to your mainframe system or to your legacy system or whatever it might be. So you can start to see those inserts, updates, and deletes in real time coming across into the event stream within seconds of it happening on the actual underlying database. Okay, now we'll talk a little bit about raw topics. So with change data capture, what happens is generally the way that you would build that, you would see data coming across, or you would have a topic per table. So for every table that you want to push out of the legacy source system, you would create a corresponding topic. And whenever a change happens in that database, we're going to push data to that raw topic. And that nice thing is it's going to push across with the entire data set every time. So if you think of every time you do an update, you're going to get a full row of a capture in time of what that record was at that time. So we do a raw topic for each database table that we're integrating with. Messages are published for every insert, update, and delete. And you get metadata on the data coming across too, as well. That's going to say, was it an insert, an update, or delete? Some of the tooling also has like previous values that you can work with. So you can have what was my state now, what was my previous state, which might help when you're trying to create business events out of these events coming out of the system. Like I said, each message contains a full copy of the record. And then the really interesting here and the big differentiator here with this is that topics can be compacted to a single message per primary key. And this is really game changing and why we can say we're going to have all that data in the event stream from a source of truth perspective. It's really going to reduce the storage and it minimizes any full loads of the system that you're going to be bringing in. So just to take a step back and talk about compaction a little bit more, a specific example might be, let's say you have a customer table in your source system. When that customer record is updated, you're going to get that full record, and with that, you're going to get an ID. Well, that ID becomes a key or a message key within the event stream. And what happens is you'll always get in the event stream each and every update that comes across for that record, but eventually it will compact down to only contain the latest message for that customer ID. So the great thing there is then you have a full capability to bootstrap from beginning all your customer data directly out of the event stream and push it into whatever data store makes sense for your data queries. So this is really beneficial, as I mentioned, and really enables you to say, okay, how much data am I going to have in my event stream, and be certain that it's not going to be infinitely growing forever from that standpoint, and which is pretty powerful if you think about some of the impacts there. It's really going to give that capability to, and I'll talk a little bit about a use case here when we get to materialized views a little bit more, but you'll have that capability to bootstrap over and over again into different downstream systems without impacting that upstream system or the source system. Okay, source aggregators. So we'll talk a little bit about source aggregators. So source aggregators is when we're taking those raw topics, and we don't just want everybody in the enterprise to have to deal with that raw data, cleanse it, join the tables together to create more of a standard model. That's what the job of the source aggregator is. So we do that once, and then we make it available for the rest of the enterprise. So we consume each raw topic for a given source, and then we build these aggregate entities. This is a concept from domain-driven design from the associated entities. So if you think about the several tables that you have, you're going to aggregate that data together. Maybe you have a customer table, you have a phone number table, an address table, some other metadata about the customer that you want. You join those tables together, create the customer entity, which is almost like a customer document. Think of like a JSON document, and you push that out to the aggregate topics. Now, one thing that's important here that's in this diagram is the aggregation state store. When you're doing those joins in real time of streaming data, you're not guaranteed the order across topics. So within a tool like Kafka, you are guaranteed order within a single topic. So that one table that's coming in, you're going to be guaranteed to get the order there. So you're not going to have stale data living forever. You always get the latest. But when you need to join with another entity, that child entity, like your phone number, might show up before the actual customer shows up. And these aggregation state stores allows you to deal with those use cases in a scalable manner. So I can join that data together in real time as it comes in, and I can decide, do I wait for the customer? Do I publish out first? Or when that full customer finally comes in, it can join to get the phone number and push out the record. So those are some of the capabilities that aggregation state store enables. All right, aggregate topics. So aggregate topics we're going to put that standardized canonical conform model in for the rest of the enterprise to consume. So again, it's a compacted topic oftentimes. It wouldn't have to always be compacted depending on the nature of the data. But you use that topic to then provide data to everybody in that self-service manner. And just taking a step back again on aggregate topics, this is where that self-service capability really comes in, because I don't have to fear somebody coming in from a self-service capability and causing a huge load on my legacy source system in order to load all the historical data into their system. They can go directly to this topic, load the data, the full data set, and push it to their whatever materialized view or whatever they're working with, their analytics. It's all available for them on this aggregate topic. When they come in and consume, it has minimal impact on the overall architecture, which is just game changing in terms of the capability to come in, self-service the data, and bootstrap into your system for the jobs that you need to run. So again, it's a real-time enterprise source of truth. It provides that place for everybody to go and self-service in to get their access to that data. Messages are published per insert, update, delete to any part of the aggregate. Each message is going to contain a full copy of all the data. And then, as we mentioned, the topics are compacted to a single message per aggregate key. And the deltas to support business events. So oftentimes you might get deltas coming across, or you could design it to get deltas across. And you might be able to say, I'm going to get business events in that case. So I might say customer updated or customer phone number updated. You might have different events within your system that need to occur when that happens. So this gives you that capability to do those types of events in real time. Materialized views. So materialized views are specifically for a lot of the APIs and microservices that you might be building. But they can consume directly off this aggregate topic, push to different materialized views. And I'm using materialized view in a term of like separate databases, not like not specifically to say like I know databases have a materialized view concept. This is different. This is just to say from an architectural perspective, we're materializing that data from these aggregate topics into views for the rest of the enterprise. So I might push it into, like I said, Elasticsearch, Mongo, Cassandra, Analytics, Snowflake, whatever it is, I can push that data out of these aggregate topics into those materialized views. And the nice thing here is that you can tailor the materialized view for the rest of the use cases you're using. So I can create APIs on top of those views. I can hide the implementation of the data store from those APIs. So if I'm working with, let's say I'm working with, I don't know, a Cassandra on-prem, and I'm moving to AWS and I don't want to manage Cassandra, so I'm going to move to DynamoDB. Those APIs, they don't need to change at all, right? Just the implementation, you can bootstrap that data to Dynamo. You can change your microservice queries from Cassandra to Dynamo, and you're ready to go with no impact to consumers. So it really provides a lot of benefit from that perspective. The other nice thing I'll talk about is oftentimes you think about what might happen if you add new fields to this type of store. Well, if you add new fields, you might need to do a full load of the system again. Well, with these materialized views and API versioning strategy, you can create APIs that are reading off that current materialized view while you're in parallel running and populating a different version of the view, whether that be in a different database or maybe it's in the same database. Maybe you're using Elasticsearch and you're adding a field to the mapping, so you're re-indexing the data. Well, you can do that in parallel to the live stream and then do blue-green type deployments to say, okay, let's test out this new data store or this new index or whatever it might be. And then I'll flip over to the original index. I'll flip over once I've done all my testing, make sure all the data looks good, and with zero downtime and impact to any consumers of the API. So again, materialized views, we're going to consume the data from the aggregate topics, the views accessed via APIs, data store technologies selected based on the required query patterns that you have. So again, picking the optimal technology for your use case, and they're bootstrapped and versioned via those compacted aggregate topics. Okay, and APIs, if we just take a drill down on some of the APIs that we've done in this space, you know, we have these various API consumers. We work with different API gateways to provide that data. And then GraphQL has been a really great tool in terms of creating relationships between some of the aggregate entities that you have. So GraphQL API provides that ability to build resolvers that know relationships between data. And then it also allows consumers to say, I want to only consume and receive, consume specific fields. So they might get query optimizations if they only need a small subset of fields, and it's all built into the GraphQL. We could do a whole presentation on GraphQL as well, but it fits really nicely into this architecture as you're starting to, at the API layer, starting to aggregate some of the different entities that were built out of the stream. Data storage. So one thing you'll notice with this architecture is there is a large amount of data storage. But I think there's a lot of thought that's been gone into, and there are some trade-offs between storing all the data at these different layers, and that's something we can talk about with organizations as well. What makes sense for your enterprise and your use cases in terms of what needs to be stored. So if you look at this, we're storing the full data set as raw data. We're storing it in the aggregation state store. We store it in the aggregate topics, and we store it in the different materialized views. So each record is stored 4 more times, and oftentimes, if you're dealing with distributed data stores, you have 3 replicas as a best practice. So you're going to see many copies of the same data for high availability and scalability reasons. The source system also has the data, raw topics, aggregation state store, aggregate topic, and materialized view, 1 or more. Within that materialized view, you might be storing it multiple times too as you're versioning your APIs. So you've added a new field. Not every time you add a new field would require a different version, but sometimes it would. And if you do add a new version and a different copy of that data, you're going to end up with another copy of that data as well. Compaction benefits. So raw topic to compaction. So if you think about this, compaction, what we're trying to do is we're trying to decrease the full load time versus trying to load so if you have to load the system completely, that first full load does take quite some time. We're building systems like this that are in the many terabytes of data. And when you're loading that data through the stream, we're writing through the stream. We've done 200,000 requests per second. I think recently we just did a million requests per second through the stream. So it really does scale and run through the data very quick at a high capacity. But it does take time to go through those full loads when you've got larger legacy systems, many tables and joins. So we want to create the ability to more quickly bootstrap that data. So that storing the data at so first off, raw topic compaction, by putting the data in the raw topic and storing it there, we don't have to full load back from the legacy system. We know that we can just start from that raw topic if we need to do another full load, that maybe there was a aggregate standardized model change or whatever it might be. Going back to that legacy system is extremely expensive. It takes a lot of time. So we're reducing the likelihood of needing to do that. From an aggregate topic compaction standpoint, we're going to get fast bootstrapping of the new materialized views. I don't have to go back all the way to the legacy system to bootstrap those materialized views. Because I've got that full data set, I can quickly re-index materialized views. I can quickly bootstrap. And it also eliminates the impact on other consumers during bootstrapping and re-indexing. If I was pushing data all the way through the system to that standardized topic again, not only my consumer for what I was needing to do would be impacted, but any other consumer would be impacted as well, as they'd see that data coming through the system again. So that's why the aggregate topic, having the full data set at the raw and aggregate topics are so important. In certain use cases, again, I'm not going to say there aren't use cases where it might not make sense to do this, but this is the reason that a lot of times we kind of start with this and then talk through it. The other thing that is available now, if you look at Kafka, so Confluent is a vendor of Kafka that has, the majority of the commits for Kafka and is one of the founders of Kafka. Are running Confluent. They have a new tiered storage capability that allows you to offload some of that data to object storage, such as S3, Azure Blob Store, Google Cloud Storage. All of those now can be offloaded. If you're running your Kafka server, you can have warm data pushed off to object storage while your more recent data is available on disk within Kafka and available to consume right away. If you think about this is, your standard steady state processing is only working on the most current data. But when you need to bootstrap that full system, then with this, it'll go back and read that data from S3, Azure Blob Store, or Google Cloud Storage, and bring it into the broker and still make it available. So it really reduces the costs, and you can scale your brokers as needed, but it really provides that so you don't have to have all the data for all time hot and available within the broker. Okay, so if we think about an alternative to compaction, what might you do? So there are some short time to live capabilities that might make sense for some use cases. So you could set up, if you're worried about your overall size of your data, of your stream data, and the tiered storage doesn't work for you, then it might make sense to just say, hey, I'm just going to store a small amount of data within the topics, and just put a short TTL on it. So you can say, I want this data to only live for a day or an hour or 7 days or 30 days, and then have that data come through. And then maybe you might back up that data. Maybe you can just pull it from the legacy source system, or you can back it up via less expensive object storage if you wanted to. And you could reduce the topics, this would reduce the topic storage and would potentially reduce your overall storage costs. This is a very viable solution, and it makes sense in certain cases. However, you do have to consider the trade-offs. It's going to increase the complexity, both from a disaster recovery when I need to do that full bootstrap or something happens. It's a different engineering process and different code that's going to be run versus what I'm doing with my standard steady state. So that's different. There's going to be some more engineering that's going to need to be done to deal with this. The replay path is rarely executed in this case too, so you're not testing things. You're not testing that replay every day like you are the steady state if you go with this short time to live strategy. It does have an increased operational risk just because there's multiple paths, and all consumers are impacted on a full load, as I mentioned earlier. So this is the reason this is just an alternative architecture that you can talk through to try to decide, hey, what's the right thing for us? Sometimes this might make sense, but there are some things that you need to consider on why it might not be the best thing for your solution. Okay, so something we also work with quite often are multi-data center strategies. The event stream is a fantastic way to replicate that data from on-prem to cloud, between cloud vendors, between cloud regions, between on-prem data centers. The replication used by Kafka via either Confluent Replicator or Mirror Maker, the open source solution, is really solid solution that provides that real-time replication of data out to the cloud. Now, the great thing about this is now you have that legacy source data pushing to cloud-based services in near real time and making it available so that you can utilize your tools or cloud-based tools to more quickly innovate on the data and provide additional value to the rest of the enterprise and customers potentially. So in this model, the legacy source is still pushing to that raw topic in the data center, and then that data center can replicate the data to a different data center or to a cloud. And then the aggregation can run in parallel. You could do this a couple different ways. So in this case, we're doing raw topic replication. The aggregations are running in parallel, and the views are available in both data centers. The nice thing about this is you can do a blue-green type deployment. So if you need to make some changes in this data center, you can make some changes and then fully test those changes, the aggregations, and then make this data center live. And it just provides a nice way to do kind of that active. You can run that active, and if you need to go to active standby to run a full load again, to add a field, to make some logic changes, you can go to active standby, run that full load, and then switch over the active to the other data center, and then the other data center can run that full load to get caught up as well, and then you're back to active. So a lot of benefits with this model of raw topic replication.
I got a question about that one. How do you address the eventual consistency issues with that kind of architecture?
Yeah, so eventual consistency is obviously something that's pretty important to account for in an architecture like this. A lot of times it's just about making sure you're working with the business to understand with them what the requirements around consistency are with the data. This data is probably, a couple seconds old as it's coming through the stream. So the data does become very consistent very quickly, but you're not guaranteed to always be immediately in sync. So a couple things in this data center to data center, you can do testing on the data that does comparisons. I'll get into a strategy there a little bit later on that to know, how up to date your data is. So there are some things and metrics and monitoring that you can put in place to see what that's like. And then when that lag is bad. So for example, in Kafka, all of these consumers and the aggregator, how behind they are. So you can set up alerting and things like that. We do this quite often in like Prometheus or Grafana to set up alerts to say, hey, I know that a lag is happening in this system, and I will and we'll try to figure out what's going on, whether I need to scale the consumers or deal with some type of data issue to help resolve it. You're gonna make that change or whatever needs to happen. The biggest thing is you got to know about it, right, and be aware when that type of thing is happening. But again, just from an overall use case, you have to understand even before you start building this system, what's the acceptable time frame within the data that needs to be consistent. A lot of times a business might say it all needs to be immediately consistent across the entire enterprise. Well, that's not always possible or feasible to do at scale, right? So you have to understand those use cases. What is the time frame? Can I have a couple seconds? Can I have 5 minutes, 10 minutes? And then understand your SLAs on that consistency. And then also understand the use cases that require that transactional based consistency. Hopefully those are happening more in those source systems versus in something that's replicating that data out to the rest of the enterprise. Okay, so raw topic replication, I think we talked through most of it. You have the active environment capabilities, right from source to the local data center. You're going to replicate your raw topics to the alternate data center. Provides maximum availability. If there is a DC outage, you're going to have that mirroring may reduce availability in those cases. Active stand availability during full loads. Blue-green deployments, full loads, and versioning. I think we talked through all those things. So another strategy might be that, I don't want to run this full aggregation in both data centers. It's expensive to run, and I want to just make my APIs multi-data center so that because it's important, I can tolerate stale data in certain cases, but I can't tolerate those APIs being unavailable for any amount of time. So in this case, I might just run my aggregator in one of the data centers and then replicate the aggregate topics across, and then I can run my APIs in parallel across both data centers for maximum availability. So another variation of this is doing the aggregation in the cloud. So this one is pretty beneficial because, when you're running the aggregation for full loads, the amount of resources that you need, the amount of compute that you need is much greater when you're running the full loads than steady state. So by running your aggregation in the cloud, you can take advantage of a lot of the elasticity of the cloud to be able to either spin up more compute while you're running in the cloud, whether it be via Kubernetes and adding more nodes and pods to do the aggregation, or just raw EC2 or compute instances. You can do that in the cloud. That's harder to do in the data center where you're buying and ordering that hardware. So this provides a nice way to do that aggregation in the cloud and come back and then bring it back to the data center. All right, materialized view replication. So this is another strategy that we see is that sometimes people are working to actually materialize the views. Or take those materialized views and replicate them across data centers. There are some technologies that have capabilities to do this. However, we don't really recommend this approach. Specifically, it's a data store specific replication It's a limited to event. It limits your ability to trigger events as well, right? So if you're replicating that data at the data store level, it might be a quick and easy solution in certain cases, but you're going to lose some of that capability to trigger new events. And then also replaying in a single data center replicates all the data as well. So that's not something that we generally recommend for people, but it is a possibility to take a look at. Multi-data center APIs, again, we're just, we talked about this a little bit. You're going to have APIs that go across both data centers. Okay, I think we've got about 14 minutes left here. So migration patterns, we'll be wrapping up pretty quickly here. So how do we migrate from what we have today? There's an incremental approach versus a big bang approach. And we always try to strongly recommend that incremental approach and talk about how is it possible to do that, to incrementally move off of that source system. So one of the patterns we use that actually I think Martin Fowler has done a blog on this is called the Strangler Pattern. So when we have those API consumers coming in, we can route that data to the legacy components and APIs, or we can route it to the new microservices. So we can predictably route, whether we do that based on a certain percentage of traffic or certain consumers or a certain data set within the consumers. We can build intelligent routers that know how to route to the appropriate legacy component or microservice to allow us to gradually move over to the new system. One thing that we've built up on that in the past is, you know, a lot of these systems you go to and you talk to them about the legacy components and what the requirements are, and oftentimes they don't know the requirements, which is really hard then to build these new microservices. The only thing they have is the COBOL code that exists today, and the people that wrote it aren't around anymore, and nobody really knows what the system does. So then how do you know, and how do you gain confidence in that new microservice or API that you've built based on the event stream? So in this case, we actually implemented this at one of our large customers where we had an API consumer and the router that we talked about, but we actually had the router routing live API requests that were going in production to the legacy component. We'd take a percentage of those requests and we'd push them to the event stream. Then we'd immediately consume from that event stream and then hit the microservice and then compare the results of the legacy component, compare the response that we got from the legacy component with the response that we got from the microservices, do a field-by-field comparison on them, and then generate metrics so that we have a real-time dashboard of what our microservice would be returning compared to the legacy component. And this solution was completely critical to our capability to actually take these legacy customers and make them live. Gaining the confidence of these API consumers to say, we're going to switch you to this whole new architecture. Gaining their confidence and buy-in was extremely critical. And when we can provide them real-time dashboards that says that 99.97% of the time, every single field is matching. And this particular field isn't matching in this case, and then we can dig into, you know, this is not matching 0.01% of the time because there's a bug in the legacy system. It's just hugely important in order to gain the confidence of those consumers and make sure that they're ready to switch over. So just kind of to summarize, back to the architectural objectives. Again, we were looking to provide a near real-time standardized synchronization of mission-critical data originating from various heterogeneous data sources, so all the legacy systems. We'll do it securely, scalable, and highly available. I think we touched today on the real-time components, the standardized components, the synchronization of that data. We didn't talk about security a whole lot, but all this communication can be secure with TLS, mutual TLS connections to the brokers. You can do encryption of the data at rest. You can do encryption of the actual payloads in certain cases if you need to. And the scalability I talked a little bit about. We're seeing 200,000 to 1 million requests per second flying through the stream, and it's during some of our full loads, and it's highly available. Like I talked about, when we talk about the event stream and tools like Kafka, you have a multi-broker distributed data storage. Kafka uses something called partitioning, so that you can scale out to multiple consumers and multiple brokers and continue to scale as long as you've got the compute to do so. So I think we've provided an architecture that really helps solve a lot of the requirements that organizations are looking for. So I just wanted to say thank you. Again, I'm Dave Reines. If you have any questions, obviously we can take some questions here if you want to put them into the chat. But if you have questions afterward, feel free to email me, dave.reines@improving.com, or Matt Russell is one of our VP of sales at Improving. His email is here as well, matt.russell@improving.com. And he told me I could give his phone number. So I didn't do that without his permission. So thank you again for everybody who's joining today. And if there are any questions, let me know, Justin.
I had one question earlier. I'm not quite sure which architecture model this was talking about. It says it sounds like this architecture is very consistent with practices such as event storming. Have you ever used similar techniques to identify requirements for these systems? Yeah,
so we have done an event storming with some of our clients. We have a VP of solution engineering at Improving that's done quite a bit of this, where you'll just have that discussion with various people within the organization to make sure you get all the stakeholders in the room. Talk about what are the events happening within the system. Come up with that common language for the organization that everybody understands. Everybody can put the events up on the board and then talk about how the system flows. And yeah, we have done some of that event storming, and it's been pretty helpful. Just a way to really get people talking and get people using the same language and coming up with that shared understanding of what needs to be built. Any other questions?
That is all the questions we have.
Okay. All right. Well, thank you again for everybody that's joined. Appreciate your time today. And again, feel free to reach out if you have any questions. Thank you.